and transferring thermal energy. And today we're going to look at the mechanism for how the thermal energy is transferred. How does heat pass from one object to another? So there are three modes of energy transfer in thermal form. The first one is conduction. The second one is convection. And the third one is radiation. So we're going to look at these three today and try to understand their differences. So the first one we're going to look at is conduction. So you might remember that in a hot object, molecules are moving fast. So over here on this side, the molecules are moving very fast. And in a cold object, they're moving slower. So at the interface between these two objects, fast-moving molecules on the left smack into slower-moving molecules on the right, and they transfer momentum to them. So here's kind of a large picture of what's going on over there. A high-energy particle with high temperature is moving fast. It smacks into an object and it bounces back, and now it's moving slower. And then this guy over here that was moving slower is now moving faster. So energy was transferred by physical collisions between the molecules, and that caused thermal energy to pass from the left side to the right side. Okay? So conduction generally happens between solids. Things that are not solid don't generally conduct heat very well. But conduction requires contact. So if you stick a piece of metal and you stick one end of it in a candle and the other end in an ice cube, we say that heat flows down the metal. What's really happening is that molecular collisions are happening all along this piece of metal here, and energy is being transferred from an area where the energy is very high, high kinetic energy, to lower kinetic energy. So the heat flows, we say. So cold is not really an entity. It's just the lack of heat. It's not its own thing. You cannot add cold to something. It doesn't flow. The energy flows, and it either flows into a system, which makes it warmer, or it flows out of a system, which makes it cooler. But cold isn't really its own thing. It's simply like a lack of heat. It's like darkness is not its own thing, right? You can't fill a room with darkness. You can just remove the light. You can't really add cold to something. You can just remove the heat. So a coat doesn't really keep the cold out because cold doesn't flow. What it really does is it keeps your thermal energy in. The air outside has very low kinetic energy, so it's cold. And if it touches your skin, then the fast moving molecules of your skin transfer energy to the air, and your skin temperature drops a little bit, makes you feel cold. So a coat keeps that transfer from happening. So this is a table of conduction rates. So these are different materials, and this number here gives you an idea of how good they are at conducting heat through collisions. And one of the things you might notice is that the numbers for metals are pretty high. So silver, copper, aluminum, and steel are all up here at the top. The easier number to use is this joule per second meter degree Celsius. And we're not going to do any calculations with these, but just in terms of their numbers, silver is a really good conductor. Copper is pretty darn good too. And aluminum's good. And steel is not quite as good. It's only 40. But then you get down to things like ice and glass and brick, and they're pretty bad. Concrete's awful. And then you get all the way down here to the very bottom, and about the worst conductor you can get is air. And air is a terrible conductor because there's just not a whole lot of molecules smacking into each other. It has a very low density. So it's hard to transfer energy through collisions when there's just not a whole lot of molecules making collisions. So you may notice that air is a poor conductor, and as a result, anything that's light and fluffy that contains lots of trapped air is also a poor conductor. So cork is wood with lots of air trapped in it. It's a poor conductor. Polyurethanes, goose down. Goose down is an interesting thing. We'll talk about it in a second. But things that are bad conductors, we call them good insulators. So things on the bottom of this list are good insulators. Things on the top are good conductors. Insulators are what you want if you do not want heat to transfer. Conductors are what you want if you do want heat to transfer. So feathers are clever little structures. They have a sort of like a straw, and it's filled with air inside. And because there's lots and lots of trapped air, and because air is a very poor conductor, using feathers or other chemical equivalents, so we can engineer materials like DuPont hollow fill and stuff that we stuff in our comforters, and it makes them light and fluffy. And air is a poor conductor, so trapping lots of air makes them very poor conductors or very good insulators. So it turns out that glass is a fairly decent conductor. And if all you had was a piece of glass between you and the outside air, heat would flow through it at a pretty decent rate, especially given how big it is. So what we do is we actually trap two pieces of glass, and between them we trap some air. So your windows at home, if you go look carefully, you'll notice that there's actually two pieces of glass, and there's air or some kind of gas in between. Sometimes they're backfilled with argon or something. But the point is that we use trapped air to keep the heat from conducting from inside your house to the outside of your house. So glass is a decent conductor, but when you put an air gap between two pieces of glass, it really slows the conduction down and makes it a good insulator. Okay, so do a little experiment real quickly. Pause the video and go find a piece of metal in your house, like maybe a door handle. Stick your hand on it and feel it. It feels pretty cold. Stick your hand now on a something that's wooden, so maybe like the wood of your door, and it doesn't feel nearly as cold. Now, it turns out that both your door and your door handle have been sitting in the same room forever, and they're exactly the same temperature, but they don't feel the same. Likewise, if you stand with your bare foot on carpet, it feels warmer than if you stand with your bare foot on a concrete floor or something like that. And again, they are the same temperature, but one feels colder than the other because it is a better conductor. So touching your metal door handle conducts the heat away from your hand fast, and so your hand feels cold. Whereas the wood is not a very good conductor and it doesn't feel nearly as cold. So you can go around your house and touch a couple things. Things that are metal that are good conductors will tend to feel much colder than things that are poor conductors, even though they're actually the exact same temperature. So that's conduction. The thing to remember about conduction is that it's physical connection or physical collisions between generally solids, but always between molecules. Convection, on the other hand, is a little different. So convection is when thermal energy is transferred by a current of fluid. So convection primarily applies to fluids, so like liquids and gases. If you have a fire burning and you hold your hand over the top, your hand gets very hot very quickly. This is not because the molecules of air are moving and bumping to their neighbors, which are bumping their neighbors, which are bumping their neighbors, which are getting all the way up to your hand. What actually happens is the air right around the fire gets heated. It has very large thermal energy, so it has a lot of kinetic energy in the molecules, and that air, because it is less dense than its neighbors, rises. So it is a moving current of fluid. So the air is rising, it's moving and bringing the heat to your hand. It would take a long time for your hand to get warm if the air was the only way the heat got there was conduction. You can try this too. You can put a pan of water on the stove, sprinkle a little bit of pepper in it so you can see it, turn the stove on, and you'll notice that the water and the pepper start circulating. The water gets hot, and because it gets hot, it gets less dense and it rises to the top, and that's how the heat gets distributed. Once it gets to the top, it cools and it flows back down. And so there's this natural circulation of the water due to the fact that the pan bottom is very hot. So there is conduction from the fire to the water through the metal of the pan. But once the water starts getting hot, the water itself moves and takes the heat with it. And so that's an example of natural convection. So natural convection is when the fluid moves because of the difference in density. So generally, hot air rises, hot water rises. So convection is the transfer of thermal energy by the current of fluid. When the movement of the fluid results from differences in density, we call this natural convection. So that's like your hand above a flame, the water circulating in a pot. On the other hand, we can simply pump or force the fluid to move, and that's called forced convection. And we do this in our house all the time. So, for example, we might heat water in the basement, and that gets the water really hot. We then pump the water through the house, and that causes all the radiators to get hot. And so the heat is being transferred from the furnace to your room by a moving fluid. So this is why it is convection. Now the fluid moves because we are pumping it, so that's called forced convection. But once the radiator gets hot, the air near the radiator flows upwards, the warm air rises, and then it cools and it comes back down. And so air will actually circulate in your room due to natural convection. The air near the radiator will go up and around and down. So this is an old-fashioned house with a radiator. A lot of times now we just simply blow the hot air through the house with a fan, and that's how we transfer the heat all around the house. So it turns out that you can see convection at work on spring break if you go to the beach. So tell your mom and dad you got to go to the beach and do some physics. During the daytime when the sun is shining, the land gets kind of warm. Let's say it's 70 degrees. The water is 65 degrees. The water doesn't change temperature very much because it has a huge heat capacity. If the air is warmer here, then the air above the land will rise. And when it rises, air from the ocean will blow in to fill its place, and it will circulate something like this. And so during the day, you'll notice the wind will blow from the ocean onto the shore. At nighttime, the ocean stays about the same temperature. So right here you can see it's still about 65 or 64 degrees, but the land cools a lot because sand doesn't have much heat capacity. And so now it's warmer over here above the ocean, and so the water rises above the ocean, and then, whoops, air comes in behind it to fill it, and it sets up a circulating convection of air that goes this way because now the ocean is warmer. And so you'll notice that at nighttime, the breeze blows out towards the ocean. And you'll also notice that right at sunrise and right at sunset, when the two are about the same temperature, the breeze almost completely stops. It is very calm right at sunset and right at sunrise near the beach. So there's some physics to try if you're ever around a beach. Other examples of convection: if there's a big concrete area or a big section of exposed rock, the sun heats that more than it heats the surroundings, and that causes convection currents to rise. And gliders or birds can circle in this convection current and get higher and higher and higher and higher without ever flapping their wings. We also use convection to keep our engines cool. We pump water through our engines, so the moving fluid carries the heat from the cylinders and the explosions to a radiator where the wind takes the heat away, and then we pump the fluid back around and around and around. So we have a radiator, we have a fan, and we have a water pump that pumps the water through the engine. So that's another example of forced convection. The last way heat is transferred is radiation. So radiation is a little harder to understand. You can think of a light bulb. If you turn a light bulb on, energy is radiated outwards. It's called electromagnetic radiation, and we'll study it in more detail later when we get to chapter 10. But for now, we just want to talk about the fact that when you get your hands near something that's glowing, you feel kind of warm. And that warmth you feel isn't being convected because the convection goes up. It's not being conducted because air is a terrible conductor. You feel the warmth beside a fire because of radiation. So you might have noticed when you turn a stove burner on, it warms up, and as it gets warm, you can kind of feel that warmth, and then eventually it starts glowing red. If you were to keep getting it hotter and hotter and hotter, eventually it would glow white. So we can't generally see heat radiated, but it's radiating all the time, and that's because the molecules are in motion, and when molecules jiggle back and forth, they send out these electromagnetic waves which carry heat or energy with them. So all objects absorb some radiation. Some things absorb radiation better than others. So here's a box, and when it's open, you can see it's painted white inside. But when she closes the lid, the light that enters the hole, it bounces around inside there and doesn't really make it back out. So it looks like the hole is black, even though the box is white inside. So what's happening is all the energy, the light that goes into this hole, it's getting trapped inside, and it doesn't come back out. So we call this a black body. Things that are black absorb radiation and don't let it bounce back. So if something is colored black, then when energy hits it, a little bit is reflected, not much. Most of it absorbs, and it makes this warm. On the other hand, if something is white, energy comes down and hits it, most of it is reflected, and a little bit is absorbed. And so generally, if you put something black and something white outside in the sun, the thing that is black will get much warmer than the thing that is white. I don't know if we'll have a chance to try this, but next time it's sunny and there's snow on your front yard, go lay a black t-shirt down next to a white t-shirt in the sun and watch what happens. Within minutes, the black t-shirt, which is absorbing the energy from the sun, will melt its way down to the grass, and the white t-shirt will just sit on top of the snow, reflecting all the energy back. It won't get nearly as warm. So we call things that absorb most of the energy that hits them black bodies. So it turns out that all objects radiate energy. The sun radiates energy. That's primarily how that's the only way the energy gets to us from the sun. It's radiation. Um, and you radiate energy too. The human body radiates energy at about 100 watts. So you're losing 100 joules of energy every second just because your body has to maintain its temperature and keep all the molecules wiggling. So if we're losing 100 joules every second, you can work out how much energy you will lose in a 24-hour day. And it turns out that in a 24-hour day, losing 100 joules every second, you will lose about 2,000 calories worth of energy, which is why, even if you don't do anything but sit on the couch, we need about 2,000 calories of energy every day just to keep our bodies functioning, because that's how much energy we need to support our mammalian temperature of 98.6 degrees Celsius. Okay? All right. So, if you want to stop heat transfer, then you need to stop convection, conduction, and radiation. Firefighters who fight fires out west wear these special suits, which are silver. That's not to keep their heat in, it's to keep the heat out. Radiation is reflected off of shiny objects and bounces away, so they don't get very hot when they're near a blazing hot, glowing fire if they wear these silver suits. You guys probably have some sort of water bottle which keeps your water really cold or it keeps your drink really hot. It uses the same ideas. If you want to minimize conduction, you have to have two walls. So most good insulating bottles have two different walls, an inner wall and an outer wall. And between the two walls, there's a vacuum. Because there's a vacuum, there are no molecules. It's just empty space. And so, because there's no molecules, there can be no conduction and no convection. So, the heat, if it's hot inside, that heat cannot get out. If it's cold inside, heat cannot get in because of this gap of nothingness, of vacuum. We also make the inside shiny. Yours might be painted on the outside, but inside between these two layers, it's really shiny, just like these guys' coats. Because if you have something hot in there, it would tend to radiate through the empty space to the outer wall. And so by making the inner and the outer wall here shiny, that reduces radiation. So those are ways you can stop conduction, convection, and radiation. Okay, so in summary, conduction, solids, physical contact, molecules transfer energy by collisions. Convection is when molecules have energy and they are transported by moving the fluid from one place to another. And radiation is the transfer of energy by electromagnetic waves, which can travel through a vacuum and which result from molecules wiggling because they're in motion. Okay, so that's our quick summary. We're not going to cover those in any more detail. We're not going to solve problems with those, although there are cool equations which describe conduction, convection, and radiation. But that gives you a feel for sort of the concepts involved and how they work. Okay?